Vincent is, I think, a 3-4-time PyData Eindhoven speaker, 5-time even. There's a reason we keep inviting him back, because generally his talks are quite enjoyable. I hope you'll find the same. Please give it up for Vincent.
So hi there, bonjour. My name is Vincent. As of recently, I've started working at a company called Probable, or as the French like to pronounce it, Probable. And there's a bunch of Scikit-Learn maintainers that are colleagues of mine. And as I was thinking, like, what would be maybe a fun talk to do for PyData Eindhoven, I think it would be nice to talk about that feeling that you get that, oh, wait, Scikit-Learn can do that? Because that's a feeling that I've been having for the last 10 years. And the reason why I think it's so interesting to talk about that specifically is because whenever I ask someone, like, what's the first thing that comes to mind when you hear about Scikit, everyone just kind of goes, oh yeah, that's fit predict. And that's not necessarily wrong, right? Like, the pipeline API that facilitates this is actually pretty darn amazing. And if you think about it, like 10 years ago, this was kind of like a tectonic shift to maybe build systems this way. But there are also other things that I would like to talk about that Scikit-Learn does. For starters, though, I figured it would be good to maybe start by celebrating a very nice pipeline feature that's not necessarily well known. So what I've got here is some code that you've probably seen before. Like from Scikit-Learn, I am importing this function makePipeline, which allows you to make a pipeline. And then inside of Scikit-Learn, we have all of these estimators that kind of behave like Lego bricks. And what you can do is you can sort of just hit the angle, but you can kind of click stuff together. Like, I've got a TF-IDF vectorizer that turns text into like a sparse representation. Then I've got a truncated SVD estimator thing over here, which turns that sparse representation into something dense. And then I followed it up with a logistic regression that also has a hyperparameter. So far, so good. You kind of look at this and you go, yup, this is the Scikit-Learn that we all know and love. This is a pipeline. We can do fit predict. And you even get a fancy representation these days. Like, if you do this in a Jupyter notebook, there's a nice little HTML that emphasizes that this indeed is a pipeline, this, then that, then that. So this is all sort of well and good. But typically, if you take a pipeline like this is not the whole thing. Most of the time, if you're doing something serious with this, you also want to make sure that the hyperparameters, which, by the way, we also visualize these days, that those are like up to snuff. You want to do some grid search typically, or even better, randomized search. But the thing with these pipelines is that quite typically, you never just use the pipeline. It's typically followed up by this hyperparameter search after. And if that's going to be the case, then we can kind of rethink the pipeline. Because imagine that we're going to be doing a grid search on the hyperparameters for this component as well as for this one, right? Well, then technically, I am recalculating the TF-IDF vectors every single time. I'm recalculating some truncated SVD for some sort of number of components every single time. Depending how big your grid is, that's a whole lot of stuff that you can actually just go ahead and cache. So I'm going to make one small change to this pipeline call, and that is that I'm going to attach a memory. When you attach memory like this, we will actually, and I say we, sort of we as a community, we can benefit from a folder on disk that is going to store the cached representations of the data set that goes into all of these components. Everything will be cached except for the last component in the grid search chain, so to say, because that will always have to be recomputed. It doesn't really make sense to cache that. But this can be a pretty decent time saver. I have a demo grid search where I do some number of components for the truncated SVD. I'm using logistic regression. Note that I'm using log space, by the way. If you're dealing with hyperparameters that are regularization coefficients inside of Scikit-Learn, it helps to take the exponential effect into account. But all those details aside, if I were just to take this grid search and with and without caching on the data set that I used that I had locally on disk, that's about half the time. So if you want to speed up your hyperparameter search with a factor of 2 when you're working on a single machine, this can actually be a pretty nice boost. And most grid searches on the internet, I've not done the full scraping thing, but I will bet you they don't use this feature. And it's such a nice one, because it does really save time. There is a small caveat to this. It doesn't always save time, because in order to make sure that we understand the data going in and out, there's a bunch of hashing that needs to happen, and hashing a very big NumPy array is also computationally a bit intensive, so it's not always a guarantee. But whenever you're doing something on a single machine, this just makes a whole lot of sense. So yeah, Scikit-Learn can do that. Scikit-Learn can do caching. And before joining Probable, I actually was not aware of this feature. But then, again, Scikit-Learn can definitely do that. But there's other cool pipeline stuff that you can do as well inside of Scikit-Learn. I'm going to be tooting my own horn a bit, because this is an open source package that I maintain. There's a thing called embedder. It is a way for you to get embeddings inside of Scikit-Learn. And just like we have a TF-IDF vectorizer where text goes in and something sparse goes out, we can also do a similar thing with the sentence transformers from the sentence transformers package that some of the folks at Hugging Face maintain. Pretty similar idea, really. So text goes into this guy, and we get some sort of dense representation out that can go straight to a logistic regression. So Scikit-Learn can definitely do BERT stuff, but coincidentally, we can also do image classification using the same trick. Embedder has a component that allows you to load an image. So image path goes in, Python image object goes out, then Python image object goes into the clip encoder, dense array goes out, and Bob's your uncle. We can also do image classification inside of Scikit-Learn. Scikit-Learn can also totally do that. So at this point, I hope that I don't have to explain to you that pipelines are super cool. Also because of this ecosystem of tools you can just go ahead and download. You can always pipeline your way out of a situation, is kind of the feeling that we have. But if you were to ask me, like, what's the real thing that Scikit-Learn does that's really, really cool, it is, like, sure, the pipeline is epic, but some of the stuff that Scikit-Learn really does is just invisible. And to maybe explain that and to also maybe help you appreciate that, I'm going to talk about what might be the simplest component inside of Scikit-Learn, which is the StandardScaler. And this is like a thing most data science textbooks always love to talk about. So the thinking is that we're dealing with some sort of classification use case. Someone in the enterprise wants to separate the blue dots from the orange ones, let's say, right? But then you do have this weird thing where the axis over here, like the numbers that we've got, this can be not balanced compared to the other axis, right? Like one dimension has just super big numbers and the other one has super small ones. So we'd like to standardize that so the two axes are more easy to compare. And how do you do that? Well, there's many ways of doing it, but the standard way of doing it is to say, take every data point, subtract the mean from that column, divide by the standard deviation. And then it's not always going to be epically perfect, but you are going to get something that's way more standard than before. Okay, so then you think, how do you implement this? Well, it can't be that hard because you just do the numpy.mean thing on each column, subtract that, then you divide by the numpy standard deviation thing. Like that implementation feels relatively straightforward. So let's have a quick look at the docs then, just to get a bit of an impression of what's happening under the hood. So for starters, you can see that apparently we can choose to only scale the mean or only the standard deviation if we wanted to. You kind of go like, all right, there's an if statement extra there, but so far still not that complex, right? But then you look at the fit method. And then there's a couple of things that are already kind of non-standard. For starters, there's a sample weight thing. So the fit methods inside of Scikit-Learn can actually accept more than just x and y going in. There's extra arguments that you can pass these days. And sample weight is a method, not a method as in Python function, but a method as in technique. But it's a technique that allows you to say, well, some data points are just a little bit more important than other data points, and I'm going to give them a higher weight. So how would that work? Actually, that might make the implementation already a bit more complex. Well, in math, it's actually not that hard because you just say, well, I'm going to attach a sample weight to every data point that I've got before I do the averaging and stuff. So, okay, the StandardScaler does a bit more than average, but this is still not necessarily something to write home about in terms of complexity. But okay. One thing that I do want to emphasize here, though, because it's a new feature that's related to that sample weight. Suppose now that I've got a pipeline that has a StandardScaler and a logistic regression. Both of these allow for a sample weight in the .fit call. And up until recently, you weren't able to then put that in a pipeline and then pass those sample weights to the pipeline. That is something that's actually relatively new. This feature is called metadata routing. So if you have components that have very specific keyword arguments in the .fit call, then you can actually pass that on using this double underscore syntax. Okay. Okay, temperature is important. But you can actually now use this double underscore syntax to say, oh, the sample weight from the standard scalar, that's given by this variable over here. So if you want to standard scale the logistic regression, but not the standard scalar, or apply sample weights or whatever order, you have the freedom to do that now. This is a new feature called metadata routing. I believe not every component has full support for this, but Scikit-Learn can do that. That also means that if you have custom components with custom arguments you're going to pass in, Scikit-Learn can also do this in your pipeline as well. And there's a couple of really nice constraining features if you're into operations research that are really cool to do there. But okay. Sample weight, cool. We have metadata routing. Scikit-Learn can do that, but it feels like easy stuff to implement, right? Well, let's have a look at what we actually accept. So X can be an array-like, but it can also be a sparse matrix. And that's also a thing that Scikit-Learn does quite well. So sometimes you're dealing with, when you're dealing with text, like text goes in and you want to represent it in numbers somehow, then very typically you end up with this array with lots and lots of zeros and a couple of ones somewhere. And if you want to store that in memory in an efficient way, it makes no sense to store all those zeros. So we're just going to store the indices where there's actually a number that appears, so to say. Okay, so this is a sparse array, and it has lots of memory features, also some speed features. It's great that we also support this. But then if you think about the standard scalar, this will go wrong. Because if we're going to subtract the mean from a sparse array, one column might have a few ones and lots of zeros everywhere, but if we subtract like the average, it's going to be a small number. And suddenly, you're going to turn all the zeros into a minus super small number. So if you're going to apply the standard scalar onto something sparse, you're at risk in turning that into something dense, and that is why the standard scalar also allows you to say, I don't want to scale by the mean, but I do want to scale by the variance, because that's a feature that's going to be important if you're going to be dealing with sparse documents. Because even if we don't care about the mean, we can still care about the scale. Use case might be dealing with stop words or something like that. And this is kind of like an edge case, but this is something that Scikit-Learn tends to do for all of its components. It tends to have you covered for all of these weird edge cases, especially if you're also dealing with sparse data structures, because things just work a little bit differently there. But it's not even like the hardest part about the standard scalar, if I'm honest. So the standard scalar also features this method, which a couple of other Scikit-Learn components do as well, which is known as this partial fit method. So we all know fit predict, but there's a different variant of that called partial fit. And the thinking on that one is that usually you just keep everything in memory, like X and Y, big hunky thing in memory, and train on the whole thing and go. But what if that doesn't fit in your memory? Like we can come up with data sets that are big enough to fit on your disk, but not big enough to go into your memory. So what you then want to do is you maybe want to think about sort of more of a generator approach where, okay, I have my first batch of the data. I'm going to train a model. I have some weights over here. Then I'm going to sample a new batch of data, and I'm going to update the weights that I had before. Keras does this a whole bunch, like anything that can train on a generator does this. But Scikit-Learn also has support for you to train out-of-core data sets. You just have to call the partial fit. But how does that work with the standard scalar? Okay, like the thing that's a little bit tricky here is hopefully we can't really do the NumPy standard deviation thing anymore. Because if I look at the formula, right, how do you calculate the standard deviation? Well, you need the mean. Oh, but we're doing this on micro batches, so the entire mean is not known up front. We can't do that. But Scikit-Learn does support the partial fit. So it turns out there's a lovely field in computer science that deals with this. So what you can do, and this is a fun algebra exercise, do this at home, but you can rewrite the formula. Like if you do the algebra right, you move the sigma around, you can move the things around, but then you do get into this formula where you don't have to keep track of mu at every point in time. You can also keep track of the sum of xi squared and the sum of xi, sorry, the square of the sum and the sum of the squares. If you keep track of those two numbers, you can also calculate the standard deviation and the variance. We have math that can do that for us. And to maybe prove that, to show that this actually does work, what I did is I made a bit of an implementation inside of just Python. So a generator is going to go out. I'm keeping track of the sum of all my x values. I'm also keeping track of the square, so to say. So I'm doing all that good stuff. And just to show that the math behind this does kind of work, I'm generating some random samples. I'm sort of streaming through this with my little standard deviation tracker. And you can see that eventually I get to about the right mean and the right standard deviation. So the input data is mu is equal to 10 and standard deviation is equal to 1. It takes a while to get from the cold state to the hot state, but you can see that we totally do converge. And you try it a bunch of different numbers, and it does all make sense. Like mu equals 1 in this case, standard deviation equals 10 in this case, the left and the right chart, all this stuff is good. Except, we're talking about StandardScaler here. So the data going in is not standardized. So it could very well be that the x value that goes in is redonkulously huge. So let's go for like 10 to the power 9. And the whole thing breaks. And this is what this is kind of my favorite intersection of a bunch of sciences. You can have the math and you can write the formula down, and in the purest form you are technically correct, but if you're in computer science land, we are squaring a number here. And if you're going to square a ridiculously big number, then the integer is going to overflow in your memory and you're dead in the water, basically. Like, this algorithm will simply not work for any big numbers out there. So you'd be dead in the water if you implemented the StandardScaler this way. Thankfully, like, math isn't sufficient, you have to know more. But thankfully, there is also an alternative. You can, again, do the rewriting thing of the math to make sure you don't need to square a number. You can also track it differently. It does require a bit more math, but Scikit-Learn does this for you. You do not have to worry about any of this. We have decades of computer scientists thinking about this thing, and decades of computer scientists to implement this inside of Scikit-Learn. And this is one of those super easy things that will ruin your day if you have to implement this yourself. So just to emphasize, like, if you're using the standard mathematically pure implementation, it totally breaks down. But if you take a step back and you use this alternative, then we do have the behavior we want. We can do partial fit with a StandardScaler, one data point at a time even if we wanted to, which is not what I would recommend, but like theoretically we do want to support that use case. So if you want to have fun deep dives, by the way, if you go to the Scikit-Learn documentation page, sometimes we will even tell you where we found the implementation, like the formula and the paper that actually tells us how we implemented this. We try to make a reference to it because also it'd be a shame if you wanted to know more about this, you also kind of want to know where the knowledge comes from. So if you just feel like learning some stuff, just really go deep on the Scikit-Learn docs. There are lots of outgoing arcs into other resources that are important if you want to understand this stuff. Note that this is a paper from 1983, so it's decades of computer science stuff that we're taking into consideration here. And like, another really fun fact about this, by the way, if you want to like good coding practices, if you go to the StandardScaler and you go to the fit method and you look at how it's implemented, it is one call to partial fit. And that also makes sense. If the entire batch fits in memory anyway, that's kind of like calling partial fit once. The only thing we do is we reset the state just before that. But if you want to understand like pretty cool implementations as well, like, the code is pretty cool to do too. So if you want to learn some code tricks or good practices, Scikit-Learn can do that for you if you look at the implementation. So why am I doing a deep dive on the StandardScaler? Vincent, shouldn't you be talking about LLMs? Well, this is visible, right? That isn't. Like Scikit-Learn, now that I'm like hired to go deep here, trust me when I say that 99% of the cool stuff that it does for you is actually invisible, and that's also kind of the point. The point is that you can just call fit predict without worrying too much about it, but that's not all that Scikit-Learn does. It's all the stuff under the hood that's actually pretty interesting as well. And it's kind of also the beauty that you don't have to be, I mean, you can definitely appreciate it, and I think that's good, but you don't have to worry about it. And that is something that Scikit-Learn can really do. And hopefully by just emphasizing this a bit, you're also going to look at the release notes a bit differently. like a few months ago, sparse support was added for k-means, just to give like a example. And especially when you consider that this partial fit stuff and this sparse stuff is actually not that super obvious, you're going to appreciate a lot of these little details that are in the release notes. Also, the solvers get better and better over time. So also implementation, yeah, the solvers get updated. There's lots of efficiency improvements on your behalf as well. But if I were to maybe give like the coolest demo of what I think Scikit-Learn can do that's really non-standard, I will have to show you something in real life. So, do I have this? Yes. So, a while ago, I made this website called Archive Front Page. The whole point of this website is that I'm scraping archive, and then every day there's a classifier that's checking, is there a paper that I might be interested in? And it's based on topics. So I do things like, is there a paper about active learning? Because I'm kind of interested in that. Is there a paper about a new data set? Because I'm typically kind of interested in that. And the way this works is like the whole MLOps thing is just the GitHub Actions, but I scrape, then I apply my classifier, and then I update the GitHub Pages thing, and I can have a look, and you can see sort of there's a sentence classifier, so each sentence kind of gets nice and highlighted. So if I see a mistake here, I can relabel, and my classifiers get better, etc. But this is kind of my way of getting cool articles in my brain, basically. That's why I built this. But the issue with this one is that this only looks at new papers. Like the newly published stuff, that's the stuff that's going to get passed here. And if Scikit-Learn taught me anything, maybe the coolest stuff happened in the 80s. So it'd be a shame if I were to miss out on that. So what I figured I might do is I figured let's build a search engine just for me. Like, I don't care about the rest of the internet, it just has to work for me. I downloaded 600,000 abstracts from Archive. You can go to Kaggle and you'll get the full dump. And I tried a whole bunch of sentence transformers. I think the one that I'm using now is just the bland Matrushka one. And I figured, let's make myself a better search bar. So I have a LansDB running on disk. I'm doing this everything with brute force, so it's going to be a bit slow. But let's say that I'm interested in doing something like this famous data set has bad labels in it. And then I hit search. And again, this is doing like the brute force thing, so this is going to take a small while. But then, after it did the vector search and comparing against 600,000 something something, I get some stuff back. And I can have a look. I can scroll around. But what I can now do, and I think that's kind of interesting in this age, notice that this is not a search bar; it's a search box. So I don't have to Google terms. I can just prompt here. Like, I can actually be a bit more expressive, and I can sort of be vocal about the vibes that I'm going after. So I could also write something down like, we should not have bad labels, because I want it to be emphasized that would be bad. And maybe something like, label quality is important for downstream tasks. It's a much more elaborate prompt. But one thing that's kind of cool is I can have a look at the results I get back, try and figure out what my prompt catches and what it doesn't, and then update the prompt. And searching kind of becomes a session instead of a single search. It's two-way communication. But the thing still remains that Archive is full of jargon, and I don't know what words to use sometimes. And even though I've got embeddings at my disposal, it's sometimes still not enough. And I have found that sometimes it's just so much easier to sort of look at a thing and kind of go, oh yeah, this is totally what I'm after. I'm going to want to give it a positive match there. Identifying mislabeled instances and classification datasets, that is so what I'm after. Positive match. I'm going to scroll down to the bottom. Token graph modeling, novel labeling strategy. Yeah, that's not about bad labels, so that's a negative match maybe. Multi-source hierarchical. Okay, that also sounds negative. But the cool thing here is that I have two methods at my disposal to narrow down the search in a session. This is a UI thing that I'm going for, not just a ML thing. I'm not throwing more tensors at it. But if I were to search now, these labels are also going to be impacting the search results. This was built in like a few hours. And the reason why I was able to build this had to do with the way that I'm going about that labeling bit. Because that's something that Scikit-Learn can do for you. So the way it works is I have a LansDB instance, query goes in, vector, I get like 1,000 vectors back. And the whole thing that I need right now is I need some sort of system that can just sort those on my behalf based on the labels that I've just given. So how can we do that? Well, play in window, and then make this bigger. Here's the thinking. So just a theoretical exercise. Suppose that this was a classification use case, and you can see over here, like, I have 2 big circles, and I have 1 data point that's labeled. Because I'm dealing with a low label scenario here, right? Like, I've barely got any labels when I'm doing this live searching thing. What a classifier would then do, if it was very naive, it would just make like a separating line between here, and that's how it would come to a classification. And in this case, you would kind of go, well, that's no bueno, because I'm interested in using the clusters inherent in the data. That's kind of the point. But lucky for us, Scikit-Learn has a semi-supervised module that has algorithms that are sort of doing a Markov chain trick. So suppose that this was my my data set, so to say. What we're going to do is we're going to look for the nearest neighbors. We're going to say, from here on, those are my 2 nearest neighbors. From here, you can kind of do the Markov chain thing, where suppose that there's an actual label here, how does that propagate through the graph? And by doing this, you can actually use the inherent cluster and graph structure to propagate the labels forward instead of resorting to a classifier, which is really just cutting a plane. Because that's honestly what's happening when you're just dealing with 2 labels. And you can go to the docs, you can see this demo, but the main thing that I hope you appreciate is the embeddings that I get back, they will have clusters in them. And this is just a very simple and quick way for me to just see if that works. If you're interested in this, it's a bit of a hidden module, but it's the semi-supervised module. Look for the label spreading algorithms that do this. It's, again, a fit and a predict, but it is also like a really huge feature that someone went ahead and implemented this. With a mere classifier, I simply did not get the quality of stuff back that I was interested in. And, like, Scikit-Learn also has metrics. Like, almost any metric, like distance between 2 vectors you can come up with, Scikit-Learn kind of has it. And we also have monotonic constraints that are super useful if you're interested in like not doing a bad thing in production. I've got videos on this if you want to know more. We also have density estimators if you want to like calculate the probability value of a data point being sampled. We have stuff for that. There's FairLearn, UMap, all sorts of plugins. So again, the fit predict thing, that's the visible thing. But the feeling that I have that I can usually I can really Scikit my way out of a problem, I've not seen any other package do that. And just having this Scikit-Learn thing in my backpack, like appreciating all the stuff that it does for me, that makes it just an insane Swiss Army knife. And kind of the point that I hope to get across here is that you also start maybe looking at it that way, because again, the fit predict thing, that is super visible, but Scikit-Learn is a whole bunch more, and it'd be a shame if people weren't aware of that. Thanks for listening. I work at a company called Probable, and on my Probable, it's also fine. I just want to make sure my French colleagues hear that I'm learning French. But on behalf of my employer, I also help maintain a YouTube channel. And what I try to do there is, besides running a podcast where I talk to like open source maintainers, a new episode going live next week, I also try to do some live streams as well as just some short explainer videos about these things that just deserve to be understood about the Scikit-Learn ecosystem that might otherwise be underappreciated. So if you've learned anything during this talk, and the thing is go to this YouTube channel, I'd also be super happy. But more than anything, thanks for listening. Ask me anything. I'll be around with the conference.
Thank you, Vincent. I think that was a very insightful presentation. I learned more about the internals of Scikit-Learn.
From the StandardScaler.
Exactly. Room for questions. This is my last session chairing this, so I will once again remind you the questions are 1 or 2 sentences and end with a...
Question mark.
Question mark. There we go. Who has a question for Vincent?
I'm also well aware that I'm between you folks and lunch, so if people want to...
Oh, yeah.
But I think there's one question.
Yeah, thank you, Vincent. Very nice presentation, like always. Yeah, you show some internal workings that we don't need to worry about, and that's very helpful when like you have complex situations and it's already working for you. But how do you know that the problem you're having is actually dealt by a library? Do you need to dig into the details, or are there some shortcuts to figure out like, oh, that problem, that's dealt with, I don't have to worry about it?
The best advice I have in this domain is just never ignore the warnings that Scikit-Learn gives you. Like, just no, honestly, because so if you see a message that says, "Hey, the model has not converged yet," then don't look at the grid search results even, like, because they're meaningless practically. That's the best advice in general that I can give you, because I am aware of the fact that the rabbit hole just goes super deep. One thing I do think is fair to mention is the library is really well maintained and the documentation is well above average. So just be aware that if you feel like you might want to go a bit in depth because you are really relying on this one feature, right? That feeling, you can always just try and do that. There's also like Discord servers, and I also take requests. Like if something is just bothering you and you want a YouTube video for it, you can kind of come to me. But it's also kind of a personal interest thing. Like I also don't want to suggest that you have to learn all these internal numeric mathematical details if you're just really not interested in it because you just want to build a regression for plants or whatever the use case is, right? But just don't ignore the warnings. Just please don't.
So thanks again for an inspiring talk, Vincent. I have a question which probably built on your previous answer. So you say the documentation is well above average, and you show that it's a lot of rigor in writing the code and thinking. Mm-hmm. Since it's an open source project, how does the team ensure that this culture is passed on from from each generation to the next one of developers? So
there is a weird. So I am not a Scikit-Learn core maintainer, and my experience thus far is that each Scikit-Learn core maintainer will give you a different answer. The Venn diagrams definitely overlap, but everyone has a slightly different concern. One thing that is happening in the background is there's like a mentorship thing. Like the thing is, someone's probably not everyone's going to want to maintain Scikit-Learn for 20 years. Like there's going to be people leaving and people coming in. But it is a nice idea to have people coming in with just a slightly different perspective. And I learned this at a different employer back at Rasa. The fact that we've all got fancy MacBooks is great, but maybe a lot of people in other parts of the world are dealing with a laptop that only has 1 gigabyte of memory, right? You can imagine if someone with that background goes to Scikit-Learn and says, yeah, I care about that partial fit thing, right? Then movement in that direction of the library is going to happen. But it's always kind of a balance. You want people to be welcoming and coming in, but you also want to add new features as quickly as possible. But there's definitely mentorship programs and hackathons and all sorts of stuff that people try to do just to get people in. But being a Scikit-Learn maintainer is also like a lot of work. So I also don't want to force people to do it or anything like that. But it's an ever-going, everlasting, ongoing conversation. The one thing I can say about the docs is that Probable actually employs one person whose main concern really is just the Scikit-Learn docs. And that backlog is growing quicker than it's getting empty. I am going to do a podcast with him soon because he also built a recommender for the Scikit-Learn docs that people just assume is manually curated. But you can use Scikit-Learn to build a recommender for the Scikit-Learn docs. That's like one thing we've done. Cool story. Sometime later. Okay. Any other? Okay. So one question before food.
Yeah, just a quick question. I couldn't find it from the Google. Is Scikit-Learn also thread safe? Basically.
Thread safe, like what?
Yeah.
What
for example, just like using for parallel grid search or something like that.
Right. So there's different ways of doing grid search. So a lot of that depends. Like you can use array cluster.
Yeah, but my question is that for grid search, it's just is Scikit-Learn thread safe? Then we can use it for other application, not necessarily for grid search.
I mean, I want to be a bit careful here because there is an issue tracker for joblib, which is the underlying library that we use, and there might be something that makes it not thread safe. But so far, I've not really had many issues with it. Caveat, though, you can use many different backends. I remember someone writing a MapReduce backend for Scikit-Learn because they wanted to do MapReduce jobs using Scikit-Learn. And then, yeah, I don't know how thread safe that was because they were using MapReduce, which is a Java environment. And then, but in general, I'm comfortable saying it's one of the most well-maintained libraries, and if there is a serious threading issue, either it will have already been solved or people will be gladly jumping on that.
Vincent, thank you again very much. One for your collection.
Yes.
You should have a few by now.
Yes. Amazing.
Thank you, Vincent.
Thank you.